Hi everybody, today we're going to work on a little project to see if we can build a small precision constant current source which has two switchable currents, 1 milliamp and 10 milliamps, which I could then use to check the calibration of a digital multimeter. My main requirements for this is that it's simple to build, it's cheap and easy to calibrate. So let's have a look at how we're going to go about this. At the heart of this project today we're going to use a small two-terminal programmable constant current source IC manufactured by Linear Technology. The one in question we'll be using is the LT3092, which has an initial accuracy of at least 1%. So let's have a closer look at this IC and how we're going to use it today. Here we see an overview of the IC in question today, and internally in the IC there is a precision 10 microamp current source. There is also a voltage follower amplifier circuit there and a little power output stage you see at the output. The way the IC works is the 10 microamp current flows out through the set pin on the IC through an external set resistor. The set resistor is selected to provide a voltage there at the set pin of 200 millivolts. And the reason that that voltage is chosen is at that particular voltage any errors generated in the internal constant current source and any errors in the offset voltage of the amplifier circuit are cancelled out. So to obtain 200 millivolts of voltage there, the resistor R set can be determined by R equals 200 millivolts divided by 10 microamps, which is equal to 0.2 of a volt divided by 0.00001 of an amp. And if you calculate that out, that would mean that this resistor here would be 20 kilo ohms. Now if we have 200 millivolts set at the set pin of the IC, you can see here that that voltage is going on to the positive input of this op amp. And you'll also notice that the negative pin of the op amp is coming back from the output pin here, and therefore this voltage follower circuit would ensure that whatever voltage we set the set pin at, i.e. 200 millivolts, that same voltage would also appear on the output pin. So that internal circuit will actually maintain those voltage levels on both the set and the output pin. Note that the other terminal of these resistors are joined together at the output, so the circuit is balanced. If we then wanted to have 1 milliamp flowing through the output resistor there, the value of that resistor is simply calculated by R equals 200 millivolts, that's 0.2 of a volt, divided by 1 milliamp, which is 0.001 of an amp, and that will give you 200 ohms. So we now have a situation where we have 10 microamps flowing through a 20k resistor, meeting up with 1 milliamp flowing through the RL resistor. So the output here will be 1 milliamp plus 10 microamps. So let's now see how we can utilize this IC in our circuit today. Here we see the circuit we'll be using today, and it's basically the same as what you saw previously, except I've made a few slight changes. Remember, we wanted to have this point here on the set pin 200 millivolts, and remember, in order to achieve 200 millivolts we needed to have a resistance on the set pin there of 20k. Now what you'll see here is I've got a combination of resistors. I have a 1k preset, in fact two 1k presets which are switchable, and I have two 39k ohm resistors in parallel. If you put two 39k ohm resistors in parallel, that will give you an effective resistance there of 19.5k. Therefore, if you then add 1k onto that, it could be 20.5k, or if you take the slider put all the way down to 0, it will be 19.5k. So you have a 1k swing on that particular resistance there, and it's around the 20,000 ohms, the 20k ohm resistor value that we need to use. Now on the output pin here, you can see I have two resistors now which are switchable. Remember before we said if we used a 200 ohm resistor there, we have an output current flowing through that resistor of 1 milliamp. If we were to reduce the value of that resistor by a factor of 10 and make it 20 ohms, the current flowing through the 20 ohm resistor at 200 millivolts, which would be there, would be 10 milliamps. You may also remember that we have 10 microamps flowing through the set resistors here, and on the output resistors we have either 1 milliamp or 10 milliamps, and therefore the output current here will be the 10 microamp plus either the 1 milliamp or the 10 milliamp current. And that's the reason I have introduced some preset resistors here, 1k, to give us some trim on this 200 millivolt voltage. By trimming that voltage we also trim the output voltage, and if we trim the output voltage we trim the output current flowing through these two resistors. And the reason behind this is that we can trim out the 10 microamps that's flowing through that network. Therefore we can adjust these preset resistors here to give exactly either 1 milliamp or 10 milliamps output. So this circuit will give us a precise 1 and 10 milliamps output we require. What we also now need to do is have a simple way of calibrating these two resistors. On most multimeters you buy today, the voltage ranges on the meters are very accurate, and therefore what we're going to do is use the voltage range on a multimeter to calibrate this current source in this circuit here. And the way we're going to do that is we're going to add a resistor on the output and measure the voltage across that resistor. So let's just put that resistor in. So what you see here is I've added the 100 ohm resistor in series with the output current, and we can connect a voltmeter across the resistor to use for calibration purposes. For example, if we wanted exactly 1 milliamps coming out, the voltage across that 100 ohm resistor would be equal to 100 times 0.001, which equals 100 millivolts. So by trimming the preset resistor there, so we get exactly 100 millivolts across that resistor, our output current will be exactly 1 milliamp. And you can see from that that we've now trimmed this circuit and adjusted the 200 millivolts here slightly to cancel out the additional 10 microamps we would have normally had and give us the exact 1 milliamps coming out. If we then flick the switch there and there to the 10 milliamp range, we can now trim the second preset resistor, but this time remember we're looking for 10 milliamps coming out, and if you put 10 milliamps through a 100 ohm resistor, you will get 1 volt across that resistor. So you're trimming the second trimmer to get a reading of exactly 1 volt. And this is how we will calibrate the unit once we've built it. Now this particular IC can be powered from any voltage from 1.2 volts to 40 volts. It's a very wide range. And what we're going to do is power it from 3 volts because I'm going to use 2 AAA 1.5 volt cell batteries. So here now you see the complete circuit diagram that we're going to build today. And you'll also notice that the way that the battery is connected, you don't really need an on-off switch, because without any current source connected here, there is no current flowing through the circuit, and therefore the battery is disconnected. However, for completeness, I am going to add the off position on the switch because I also want to have a LED indicator. So what I'm going to do is break the circuit there, and we'll simply put a switch contact in there. Now here you can see I've added all the switch contacts there. I've added a green LED and a series resistor with it of 560 ohms, and that's connected to the other side of the battery. So when the switch is on, the LED is on, and you'll notice here I'm using a 3-way switch. 2 positions are on and 1 is off, so that position there is off. But as I mentioned before, you don't really need a switch because the circuit is already open circuit without a switch. So if you didn't want to use the LED on one that you build, then you could leave this arrangement off. However, I'm including it because I'm going to use a rotary switch that has sufficient contacts on there to handle this. So what you'll see here is that this 3-way switch here is connected to, ganged with that one, which is ganged with that one. So you'll see I have another contact there which is open, so we go from the off position to the 1 milliamp position to the 10 milliamp position. So here you see now the final circuit we're going to build today. I've also indicated on the IC the pin connections. The input for the IC there, the voltage in, is pins 7 and 8. So join those 2 pins together, pins 7 and 8. The set pin is pin 5, and the output pin is pins 2, 3 and 4, which you can join together. So here now we have the complete circuit for our project today. One other point I would make with this circuit is because it works on the relationship in terms of the voltage on the set pin and the voltage on the output pin, the tolerances of the resistors is not that critical, and therefore you can use, as long as you use the same types of resistors, if they drift, they all drift by the same temperature coefficient, and therefore you get away with using lower tolerance resistors. I'm going to use today for the 39K 1% tolerance, and for the other resistors here I'm going to use 0.1%, but you could also use 1%. It's not super critical. So let's have a look at the components I propose using for this little project. Here we have the project box. I'll be using a little plastic project box with a little metal lid on. This particular one is 83 millimeters long, 53 wide, and the height is 35 millimeters. And these you can pick up for around about £1. I'll be using a small piece of matrix project board there with some pins. There we have an LED I propose to use to indicate the power on, the green LED, low current one. This draws no more than 2 milliamps with a series resistor there which is 560 ohms, and a little LED holder assembly which I'll be using to mount it into the case. There is two AAA 1.5 volt cell batteries, and there's the dual battery holder there for those cells. I'll be using two 1K 25 turn presets here. Make sure you choose good quality ones for this project. I have two 4mm banana sockets here, a red and a black one. A few resistors here. There's two 39k ohm resistors there, and these are 1%. And then I have three 100 ohm resistors. These are 0.1%, and I have two 10 ohm resistors. Again, they're 0.1% tolerance. We have a rotary switch here which I'm going to use. This particular one is a 3-pole 4-way rotary switch. For this particular project we're only going to be using 3-way, but there's an extra facility there if you wanted to upgrade this later. And I have a little pointer knob I'm going to use for the switching. Now the chip we'll be using for this project, here it is. It's the Linear Technology, the LT3092. Very small. This is in a SOT 23 package. So what I've done here is I've purchased a little board, as you see there. These are SMD to DIL, a little adapter board where I can solder that chip onto the board, and then I have some inline pins. You can see I've got them here, which I'll then use to mount it onto the matrix board. So there we have it. There's the component for this particular project. Just a quick look at the project box here I'll be using. It's got a little aluminium lid on it, which in my case I'm going to use that as the back cover. I'm going to mount everything on the plastic here. Now the first thing we need to do is actually decide how we're going to mount the rotary switch and the two banana sockets and the LED on this project box. I think what I will do, I will mount the two banana sockets and the rotary switch in line, and I'll make the banana sockets spacing 19mm, which is a standard spacing for input sockets, and then I'll put the LED probably just above the banana sockets. Right, the next thing we need to do is mark and drill the holes on the project box itself, and what I've done to enable me to do that is I've made myself a little template which will actually form the fascia for the unit itself, and I printed this on my LaserJet printer on glossy paper which has got self-adhesive sticky on the back. So what I will do, I will just position this onto the top of the box there, and the little crosshairs there I'll just poke through, and we'll mark the positions of the holes. Okay, I've now pricked the holes through the crosshair, so what I will do next is I'll take the box away and I'll drill the holes. So let me do that. Right, well here you now see I've drilled the holes in the project box here. This hole is for the rotary switch, these two are for the 4mm banana sockets, and this one here is for the LED holder. Well, there you have the project box now with the
front fascia stuck onto the top there with the holes behind. So what I'll do now is I'll where the crosshairs are, I'll just prick through and I'll cut out the holes with a sharp knife. So let me just finish that and we'll come back. Right, here we have the case now with the holes now cut out, so I can now put on the banana sockets and the LED. So the next thing to do is screw them at the back and put the rotary switch on. The rotary switch now mounted, and obviously you can see the length of the spindle there is far too long, so I just need to trim that down so I can put the pointer knob on. So let me just trim that, cut that down. Here you can see now the box with all the items mounted, and the pointer knob is screwed on. I've made sure that when I tighten the pointer knob up that the position of the switches was matching up with the indication I have on the front panel. So I have off, 1 milliamp and 10 milliamp. So let's have a look at how we now will position the components inside the box, and then we'll do the wiring. If we look now at the inners of the box and just see how we'll position the battery holder and the matrix board for the wiring. So I think the battery, first of all, will slot just down there. So if my intention is to slot the battery holder in there, and then the matrix board I have with the circuit on, I plan to have that slotted at the other side. So you can clearly now see the battery holder positions there. It clips in quite nicely, and the matrix board also slots in nicely, and it's held in place by the casing of the rotary switch. Now that will be quite good there, the matrix board, because my intention is to have the adjustment presets on there, and then probably drill little holes on the outer case here so we can trim it and calibrate it when it's complete. So now let's have a look at how we go about the wiring. I've just drilled 2 small holes there, so I have access to the preset trimmers just on the side of the casing. There you can see the 2 preset trimmers now mounted on the matrix board, together with the IC there on its SMD to DIL little adapter board there. They're now both on the matrix board. If I just tilt the boards, tilt it slightly, you can see where the trimming presets now are accessible through the casing. So what we'll do next is we'll solder some of these components here now. All the wiring is now complete. I'll just go over 1 or 2 points here. On the rotary switch there, the switch contacts there, you see we have 2 resistors in parallel across those 2 points. They're the 39k resistors. The output is taken from that point there through a 100 ohm resistor, and then that goes to the positive terminal of the output there, the banana socket. The resistor you see going across the top here is simply a 560 ohms, which is going to the positive of the battery there. Also, that is the connection on the IC for the positive of the battery, so that's pins 7 and 8 of the IC. The preset resistors here, you probably can see we have a yellow wire there connecting one side of those presets to pin 5 of the IC, and then the other side of the presets is going to the rotary switch here via these blue and orange wires, and they're coming out there and there onto the rotary switch. On the rotary switch itself, you see that the positive supply is coming out there. That goes to the IC, also feeds the, as I said, the LED, and the switch contact there is going to the battery. The other side of the battery, which is this black wire here, is going to the negative terminal of the output, the black terminal. So let me just slot the battery in and you'll see it with the battery in. There we have the battery holder now slotted in into its position in the case. I'll just tilt it down and we'll get a better view of that. Okay, there's a slightly clearer view of the battery now in position. It's just slotted in the side of the case, in between the case wall and the rotary switch. So the next thing we want to do now is test the unit and calibrate it. Right, in order to calibrate the unit now, we need to connect the multimeter here across the 100 ohm resistor, which is in series with the output socket there. So if we reverse the unit, there you can see the output socket there, the red one there, and the resistor, the other side goes to the center switch contact there. So basically what we need to do is connect the negative side to the positive wonder plug, and the positive lead will go on to the switch contact there. So we're now across the 100 ohm resistor. So if I now connect that to the meter, the meter is now connected, and the next thing we have to do is put a shorting link across the two input terminals there, otherwise we wouldn't get any current flowing through the unit. And then if we flick it onto the 1 milliamp range and look at the reading there on the meter, and at the moment the meter is reading 101.01 of a millivolt. Now that needs to be set for the 1 milliamp range, that needs to be 100 millivolts. So if I just turn the unit round so I can get access to the little presets there, and if I adjust the 1 millivolt preset until the reading on the meter is equal to exactly 100 millivolts, which is just about there, that is now set. To set then the 10 milliamp range, flick the meter now to the 10 milliamp range, and this time we're adjusting the 10 milliamp trimmer for a reading of 1 volt. So again I need to adjust this, the other trimmer now, to get a reading of exactly 1 volt. Just about there, I think. Just about there. Okay, so the calibration is now done. So let's now check the current output on the current range of the meter. So I'll just disconnect the shorting link, switch the unit off, disconnect the crocodile clips. We'll now change the meter for the milliamp range, so I'll just move the lead there to the current range output, set the meter to DC current, connect the meter now to the current source unit, and then if we flick to 1 milliamp range, well, the meter's reading 0.999 of a milliamp, which is just about 1 milliamp, and then the 10 milliamp range is reading 10.004 of a milliamp. So I think you'll agree that that's fairly accurate in terms of the output current of this little unit, giving both 1 milliamp and 10 milliamp out. So you can use this to check your multimeters on those current ranges.
Now I would point out that the accuracy of the adjustment we just made there is dependent on the 100 ohm resistor that we have as our sense resistor in this unit. The one I'm using is a tolerance of 0.1%, but if you was to get a one which had a tolerance of 0.01%, the accuracy of this unit would be that much greater. Well, I hope you found this little project of some interest. Many thanks for watching. See you all again next time. Bye for now.